Assalamualaikum and good morning, everyone. We are from Group 13 and we are going to present about the topic of gravitational and Kepler's law. But first, let us introduce ourselves before we proceed to the introduction of this topic. This is the list of our team member: Durrani Muslim bin Ahmad Tajuddin, Siti Nur Hazirah binti Muhammad Sardi, Nur Farha Natasha binti Fadil, Nur Hafiza Ali binti Idris, Nur Shamila binti Abdurrahman. In next slide. What is Kepler's law of planetary motion? Kepler's law of planetary motion is a law that describing the motion of the planets in the solar system. Kepler's law were derived by Johannes Kepler, who was the German astronomer in 1609 until 1680. There are three laws of Kepler's law of planetary motion, which are law of ellipse, law of equal area, and harmonic law. Why Kepler's law is important? Kepler's law of planetary motion marked on an important turning point in the transition from geocentrism to heliocentrism. They provide the first quantitative connection between the planets, including Earth. But even more, they mark a time when the important coefficient of the times were changing. Okay, next I will pass to the next presenter, Siti Nur Hazirah, to explain the concept of gravitational and Kepler's law.
So now I will explain about the concept of gravitational and the Kepler's law. Next slide. First, concept of gravitation. Gravitation is a force of gravity between any pair of objects anywhere. The force is proportional to each mass and inversely proportional to the square of the distance between the two objects. For the equation is we use Fy equal to G times Mi times Mj over Ry squared. For Fy is force on particle I of mass Mi exerted by particle J of mass Mj. The law of reaction requires that Fij is equal to negative Fji. G is the universal constant of gravitation, which is the value is 6.67259 plus minus 0.00085 exponent negative 11 and meter square kilogram per kilogram square. So next slide. So here I want to explain about Kepler's first law, which is law of ellipse. Law of ellipse is all planets are orbiting in ellipse with the sun located at one of its foci. Kepler's first law is developing from a general differential equation of the planet orbit in any central force field. Then it developed from the result of derivation of orbital equation of an inverse square law of force. So this is the derivation of our part. Next slide. Inverse square law. Inverse square law is the law of gravitation is called an inverse square law because the magnitude of the force is inversely proportional to the square of separation. Next. So here is derivation from the inverse square law to obtain ellipse equation. So here is the inverse square law derivation. Okay, next, Tasha. Alright, we go for the Kepler's second law, which is law of equal areas. Law of equal areas is a line drawn between the sun and the planet sweeps out equal areas in equal time as the planet orbits the sun. So this is the derivation of the second Kepler's law. We move to the third Kepler's law, which is law of harmonic. Law of harmonic is the square of the sidereal period of a planet, the time it takes a planet to complete one revolution about the sun relative to the stars is directly proportional to the cube of the semi-major axis of the planet's orbit. So here is, we go for derivation of law of harmonic. We use derivation from the Kepler's second law. All right, that's all from me. So go next to Natasha for the application of the concept daily life.
I will continue to explain about the application of gravitational and Kepler's law in daily life. Firstly is netball sports. We have all heard the stories of how Newton suddenly realized the universal law of gravitation after observing an apple fall from a tree. After seeing an apple fall from a tree, he started to consider that the apple moved faster because its velocity changed from zero as it is hanging on the tree and moved toward the ground. In this case, which is netball sport, when the ball is thrown upward, it goes up until both its velocity and the force acting on it are zero. After that, the ball then hits the ground with zero velocity and an acceleration brought on by gravity. The ball moves up with some velocity attained by the force applied by the person who throws the ball. This is restricted until uh, the force of the ball is zero. Then the acceleration due to the gravity is downward in the direction of the surface of the Earth. So we can clearly assume that an object thrown upwards comes down after reaching a point due to the Earth's gravitational pull. Okay, next is uh, global positioning system, or generally we call as GPS. The German astronomer Kepler's law made a Kepler's law of planetary motion. He provided information about the motion of the planets in the solar system. This law applies to any satellite and useful for visualizing motion in space. The satellite may be launched into either a virtually circular orbit or an elliptical orbit depending on its intended use. Similar to how the Earth revolves around the Sun, satellites orbit the Earth. Um, the Global Positioning System (GPS) is a navigational device based on a gravitational model. Okay, it can tell us where a person is and also how to get to a location exactly. Their signaling system make it possible to calculate place on the Earth. Satellite experience time passing at a different rate than object on Earth since they are orbiting high above the planet. Due to the mass of the Earth, the gravitational field that satellites experience in orbit is weaker than the gravitational field that object on the Earth's surface. This implies that clocks on board satellites and the passage of time experienced by them are different from clocks on Earth. So this effect must be taken into consideration in order to calculate GPS positions accurately. That's all from me. Next, we continue with problem and solution of gravitational and Kepler's law that we presented by Durrani Muslim. Thank you.
Okay, now I will present to you guys the problem and solutions of gravitational and Kepler's law. So next slide, please. So here's the first question. Find the gravitational attraction between two solid spheres of 1 kilogram mass each if the spheres are almost in contact. Express the answer as a fraction of the weight of either sphere given the density of lead is 11.35, and there's a hint of the formula of density. So it's also given the gravitational constant here and also gravity itself. So you can see here in the solution M1 and M2, which refers to the two solid balls, are the same mass. So it instantly applies to the given formula of density, and thus we can from that we can get the radius between the two center of masses. So using the formula of Newton's law of universal gravitation, we can get the amounts of force, gravitational force, and since the answer requested it to be a fraction of the weight of either sphere, we could divide our answer, the force, with the weight, which is equals to mg, and thus we can get F over W, or mg, equals to the answer provided here, 8.917 exponent negative 9. So next question, please. Next slide. So here's the next question. The planet Mercury travels around the Earth with a mean orbital radius of 5.8 to the exponent of 10 meters, and the mass of the Sun is 1.99 to the exponent of 30 kilograms, which is its mass. So use Newton's vision of Kepler's third law and determine how long it takes Mercury to orbit the Sun, and give the answer in Earth days. So it's already given here the radius of Mercury and the mass of the Sun, and thus all that we needed is to find the time for Mercury to orbit the Sun. So using Kepler's third law, the formula here, and once applied, it's just an apply the given information, and thus when translated into Earth days, finally we could translate into such as 1 hour is equals to 3,600 seconds, and 1 day is 24 hours. When calculated, we can finally get Mercury's time taken to orbit the whole Sun is 88.3 days. So that's it from me, and let's continue on to our conclusion from Nur Shamila.
The conclusion for this topic, which is gravitational and Kepler's law, is Newton's law of motion with gravitational force used in second law, imply Kepler's law, and the planets obey the same laws of motion as object on the surface on the Earth. And according to the Kepler first law, the planet path is an ellipse with the Sun at one focus. Although it was widely assumed at the time that the planet moved in circle around the Sun, Kepler's data proved this to be incorrect. Only by understanding that orbits are elliptical, we can begin to explain many observed planetary motion phenomena. And for the Kepler's second law, states that the speed of a planet's motion is proportional to its distance from the sun. Indeed, it states that if a line is drawn from the sun to the planet, the area swept out by that line in a certain time is constant. That this means that the planet moves more slowly when it is farthest from the sun than when it is closest to the sun. And for the lastly is Kepler's law differs from other two in that it is more mathematical than the first and second laws, allowing the period of the orbit to be calculated if the radius is known, or the radius to be calculated if the period is known. And it specifies that the square of the orbit periods is proportional to the cube of the radius, and this is applied not only for planets orbiting the sun but also for satellites orbiting the Earth, and therefore it is important in space technology. So I think that's all. Next, we will move to the Q&A session. So is there any question?
Hello, my name is Zoharmi. I want to ask, the elliptical orbit of planet were indicated by calculation of the orbit of which astronomical body?
Alright, I get your question. Your question is the elliptical orbit of planets were indicated by calculation of the orbit of which astronomical body. Alright, so by observing the motion of Mars in the sky, Kepler inferred that the planet have elliptical orbits around the sun. Kepler discovered that a simple ellipse would clearly define the orbit of Mars and eliminate more complexities. It would also eliminate the need for epicycles. So that is the answer. Did you get it, Zarmi?
Yes, thank you.
Welcome.
Hello, my name is Shohaida. I would like to ask a question. What is the constant of proportionality in Kepler's law of period known as?
So I'll take your question there. So if I repeat your question, it is what is the constant of proportionality in Kepler's law of periods known as? So there is no particular constant of proportionality for Kepler's law of periods. The law of periods only relates the proportionality of the square of the time period of revolution of a planet to the cube of a semi-major axis of the orbit of the planet. So hope that answers your question.
Yes, thank you.
Hello, I have a question. What can be improved by the Kepler's law of planetary motion?
Alright, I will answer that question. So the question is, what can be improved by Kepler's law of planetary motion? Kepler's law of planetary motion improved the heliocentric theory of Nicholas Copernicus. So it improved by replacing its circular orbits with epicycles with elliptical orbit. Does it answer your question?
Thank you. Okay, I think that's all from us. Thank you.